Alright, so we're going to learn about state machines, and just to show a nice little example of what a state machine is and why we might want to make one, I've drawn out here the stoplight in lot A. So we have food land down here, and then this is the street that goes up to the point, and then we got right here, and then we got Kamehameha Highway going here with cars going this direction and this direction right here. So we have a stoplight, and of course we want to give the highway kind of priority, leave it green as long as possible so we can let cars go by. But when a car here comes up to here, it'll have a red light, and then hopefully the stoplight will sense that the car is there, and it will switch, and for the highway the light will turn yellow and then red, allowing the car to go on a green light, and then after the car goes, the car will be gone, and then the light will turn green again for the highway, and allow cars to go on the highway. So a state machine is a circuit like before, but its input isn't just a sensor like there's a car here or there isn't a car here. It's going to be a sensor and compared with time. So when the car comes, then for a little while we want the light to be yellow. Then we want it to be red, and that's the light for the highway. And then that'll allow the cars to go on the opposite way, and then after a little while it should turn back to green. So state machines are a function of inputs, and in my example we have that a car comes onto the light on the opposite way, not on the highway. So that's the input. If there's a car there, it knows that it needs to turn red for the highway so the car can go. But the other thing that state machine pays attention to is time. So that allows things to happen in time. And so in order to control our data path, we're going to need to build a state machine so that we can turn on and off the switches. We obviously don't want to turn on and off all the switches like you've done in the data path lab. We want that to happen automatically. So our job is to build a state machine that does that, and its inputs in our data path, of course, this is for our data path. The inputs are going to be the IR register. So when we get an instruction loaded into the IR register, we can go look at its opcode and say, oh, this is an add instruction, and then perform the add instruction. And after we perform that instruction, it can go and fetch the next instruction out. So how we model state machines is with a diagram, and if you're in CS 320 and have learned about finite automatas, this will look very familiar to you. So by the way, finite automatas and state machines are close to the same thing. So we have this state right here, and there's going to be 3 states here, and this will be this state right here will be when the light is green for the highway. So I know this is a little confusing because there's lights for the highway and there's lights for the opposite side that go opposite, right? When the highway is green, we want the other way to be red, and when the other way is and the other way, of course, is going this way or that way right here. So when the light is red for the highway, then the other way can be green. I'm just going to write down the lights on the highway side, and of course we could have other outputs too. here. By the way, the light color is the output. There's actually 3 outputs. There's 3 lights, a red light, a green light, and a yellow light. So there's 3 outputs on this right here. And so the output is a function of what state we're in. So we have our 3 states, and if there is no car, so if there's not a car waiting on the other way, we should just keep the light on the highway green. Now if a car happens to come, then we'll go to this state down here, and that will turn our light yellow. So let me get a yellow color here. So that'll turn our light yellow, and then we'll stay there for one amount of time while the light's yellow, and then from there we'll just automatically move to this state where the light will be red, and we'll stay there hopefully long enough for the other cars to go by. So this can become maybe a kind of slow moving time machine, and then after it's red for a while and all the cars on the other way were able to go, we'll turn the light on the highway back to green. So again, in these states we could also map out the lights on the other side, go in the other direction, not on the highway, but from the Foodland parking lot or the road that goes up to the point. Anyways, our outputs are right here. So green, yellow, and red is the output of our circuit, and our input right here is whether or not a car is waiting to go to either turn onto the highway or cross the highway. So now what we want to do is make an electrical circuit that does this behavior right here. And so to do that, what we're first going to do is we're going to number our states. And in computer science, we always start numbering by 0. So we'll number this state 0. We'll number this state 1. And I'm going to number this final state 2. We could number it 2 if we want to, but I'm just going to number it 3 and just skip over 2. And you'll see why I do that later on. It has something to do with K-maps, but you could number it 2, but we'll just number it 3 either way. Now, of course, we're dealing with digital circuits, and we can't put decimal numbers in, so we have to convert these numbers to binary. So, and 0 is, the binary state is 0, 0. Right here, 1, and we'll number this state 3. Okay, now just because a binary and we're using 2 bits right here for each number, now we have to use 2 bits to count all the way up to 3. That actually also leaves a hidden state that we're not using over here, which I'll number 2. Okay, now you don't have to draw this state when you do your circuit, but it's there. We're just not going to use it at all. There's no arrows coming into it, and no arrows going out, so we're not using it. But now we have our 4 states. Now if we have more than 4 states, if we have 5 states or more, then we're going to have to use 3 bits to number. So then it would be 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0 for, as we number our different states. All right, so that's our, this thing right here that I drew up is called our state transition diagram. All right, so I have here something that looks a lot like a K-map. Now, it isn't a K-map. You'll see a couple of differences, but what we're going to call this is a state transition table. Okay, so what this is basically converting our state transition diagram that we have created before into a table. And so how we do that is, if you notice over here, we have our input, the car. So the size of our state transition table will vary based on how many bits we use to number our states. So we were lucky and we only used 2 bits, but if we needed 3 bits, then we'd have to, that would be 3 things that would be included in our state transition table for the states, plus 1 thing for our input, which would be the car. So, but in this case, we only have 2 bits for our state and 1 input. So it makes it this size of a state transition table. This is eventually going to get converted into a K-map. So that's why it looks like a K-map. It will make it really easy. And so what we do is, by the way, the Q's right here are the state that we are currently in. So Q represents the state we're in, and the D's over here, these D's are our output, or the next state that we should go to. Now if you notice, there's 2 of them because each state has 2 bits right there. And to fill out this table, let's first look at this state right here. So when we're in state 0, 0, you guys see that this state is numbered 0, 0 right here. So we find the states here. So notice we got the Q, and this is the state we're in, and we got state 0, 0 right here. So that's this column on our state transition table right here. So if we're in state 0, 0 and there is no car, and I didn't, hopefully you know this exclamation point, this exclamation mark right here means not. So if there is not a car and we're in state 0, 0, then the next state we want to go to when we transition states is state 0, 0. So we just fill that in right here. So I'm using different colors for each one of these, and you'll see why. It's just to help show you something later on. But we got 0, 0 there. Now, if there is a car and we're in state 0, 0, then the next state we go to is state 0, 1. You guys can see that right there. So if there is a car, then we go to state, and notice over here, that's no car, and this is on, there is a car. So that's state 0, 1. Okay. If we're in state 0, 1, it doesn't matter what our car is saying or not. We always go to state 1, 1 next. Okay, so we just fill that in, 1, 1, and it doesn't matter whether there's a car or not, so that's why I put it in both the top and the bottom. Now, if we're in state 1, 1, right here, no matter what, we go to state 0, 0. So we just fill in 0, 0 right here. And let me use the same colors from before. Now, the state that we're not using over here, state 2, I really don't care. I'm not using it, so I'm going to fill in D's for that, for do not care, and try making them not look like zeros there. So hopefully those are enough different so they don't look like zeros. Right there. Okay, so there's our state transition table filled out. I just kind of translated the information I had from my state transition diagram into a state transition table. All right, so Now what I'm doing is I created two K-maps, and let me erase this up here. Okay, so now what I did is I created two K-maps, and the reason why there's two is because there's two numbers inside of my state transition table in there. Of course, if we had 3 bits, then we'd have to use 3 numbers inside of here. Now you don't have to worry too much about that because in this class we're only going to do use states with 2 numbers. So so what we're going to do is we're going to take the blue numbers, or the numbers on the left side right here. So these blue numbers right here. And we're going to take the blue ones and we're going to put them in this left K-map over there. And then the right numbers right here are going to go into that K-map right there. Now, what that really means is the D0 right here, this D1 is going to be on the left side and the D0 is going to be on the right side. So let me go ahead and write that down. So we got the D1 over here and the D0 one right there. Now it's just important to make sure you don't mix these up. Remember, Q, or the 0, is the least significant bit, or the one on the right, and 1 is the most significant bit, the one on the left. If you switch them in one place like that and don't switch them in the other place up there, then your state transition table wouldn't quite make sense. So I'm going to take our blue numbers and put them over here, and we're going to take our green numbers and put them over here. And so again, the numbers on the left went on to the left K-map, and the numbers on the right went to the right K-map. So these are K-maps, so the next step is to solve them. And I'll do that off camera really quick. We'll just circle them, and we'll go ahead and solve them. Alright, so I've solved them. Got the one circle on this side right here, and this is the this right here is the grouping for that circle, for this circle right there. And then this circle right here gets this same grouping, and then we OR that with this circle right here that gets that part. So now we have an equation for D1 and D0 right there. So the next step is to make this circuit. Now I didn't quite finish this out. This was a Q1 not over here. So the full equation is Q1 not and Q0, and then C and Q1 not. So to make that circuit in Logisim, we're just going to go to our memory tab here, and we're going to grab out 2 D flip-flops. Since the D flip-flop will remember a number, with 2 of them we can remember what state we're in. And that is why the Q's right here represent our current state. And then on the input we put the next state that we want to go to. And then when we toggle the clock from a low voltage to a high voltage, we'll move to the next state. So right here, I'll just grab some tunnels and label these. Actually, first, why don't I label each one of these flip-flops? I'll call this one D1, and then this one I'll call D0. So we have D0 right here, or D1 right here, D0 right here. So this would be Q0, and this would be Q1. Of course, these guys are always the opposite version of this, so this will be Q0 not and Q1 not. So I'm going to go ahead and label those. Okay, so I labeled this one Q1 and then Q1 not, Q0 and Q0 not. And we can just hook these up together. Make sure we don't have a circle right there, or else we connected our D input to that. But then we can grab a switch right here, this will be our clock that'll clock both of these at the same time. So they'll both change at the same time. And then we just put in the equation from our k-maps right here. So if you remember, D1 is equal to Q1 not Q0. And if you need to rewind the video and go back and look at that, you can. But so we'll do the AND gate. So it's Q1 not Q0. So just grab tunnels and connect them through. You can also just connect the wires directly over there, but we'll go this tunnel. This was Q1 not right there, so we just connected this to that. And then we'll also connect Q0 to the other input right here. Okay, and now this one right here is Q1 not Q0 or C Q1. So we're going to need an OR gate right here. So an OR gate with two inputs and then two AND gates, one for the first circle on our k-map and another one for the second one. Right there. And then I'll just quickly hook up those inputs. So right here, we did Q1 not Q0. That was one AND gate. And the other AND gate was C Q1 not right there. So we just connected that up. Now, of course, you don't have to use the tunnels. You could drag wires around and over here if you want, but then it gets a little messy with lots of wires crossing. We do need our car input, so we'll just grab a switch for that. So, and if the switch is off, that means no cars are waiting to cross the highway, and if it's on, that means a car is waiting to cross the highway. So now we can try our circuit out here. So if we look, we're in state 0, 0, and we'll go ahead and toggle this. Every time it goes from a low voltage to a high voltage, we move to the next state. So, and that's what we wanted. If you go back and look at our state transition diagram, that if we're in the green state for the highway, that we want to stay in that green state while no cars are coming. We could see as our clock goes along, no cars are coming, and we stay in that state. Now, as soon as a car shows up, if we look at our next state now, notice our next state is a 0, 1. We're still in state 0, 0, but cars come up, and it's set off the sensor, so now we have an input saying there's a car here. And so we'll move to the next state, which is 0, 1 right there. So notice 0, 1. We're in that next state, and the light will turn yellow on the highway right there. And so we'll go to the next state right here. And just so before I do it, the next state is 1, 1, and that's the red on the highway state. And now we're in state 1, 1. And the car will now be able to go, so the sensor will shut off. All the cars going the opposite way get to go. They get a green light. The highway is stuck on red. And then our next state is back to 0, 0 again. And now we're green on the highway, and we're stuck on green on the highway until a car comes again. And then we'll go through the cycle. The car will get to go. And now we're back to green on the highway again. So that's good. Our state machine's working, but we don't have any outputs yet. So if we remember in state 0, 0, we wanted our green light to come on. So in this example, we have 3 lights. So I'm just grabbing 3 inputs, and I'll label them. One will be red, yellow, and green. Now, not all state machines have 3 outputs. They might only have 1 output in 1 state. You might only have an output in 1 state, like in your homework. So you'd really only have 1 of these when you go to do your control circuit lab, you'll do a state machine, but you'll only have one output. You won't have outputs for every state, and that's okay. So we want our green light to be on when we're in state 0, 0. So what that means is when we're in state 0, 0, just grab an AND gate, place it down. We'll grab an AND gate for all three of these actually. And we just encode the AND gate with the right state. So if we're in state 0, 0, then we want this to be on. So since they're both 0, and remember this is the state we're in, since they're both 0, state 0, 0, so bit 1 is a 0, we're going to use the not version of bit 1 for that. So I'll label this one Q1 not. And this guy right here will be Q0 not. And that's because they're both a low voltage. I'm using the negated version of them. And you see when you're in state 0, 0, this guy lights up. And if a car comes and we move to a different state, the green light shuts off, but hopefully the yellow light will turn on. So let's go ahead and hook up the yellow light really quick. The yellow light was in state 0, 1. So D1 is a 0, so that will be Q1 not. Or bit 1 is a 0, so that's Q1, bit 1 not. But bit 2 is a high voltage, so we want to use Q0 in that case right there. So we're just kind of doing the binary encoding of those state numbers right here to get this. So Q0 right there. And now our yellow light's on, but our green light is off. Of course, the next state, we're in state 1, 1. That's our red light state. And you can go back and look at your state diagram. So now we want the red light on in the highway, which will let the cars go the opposite way. And so in that case, we're in state 1, 1, so they're both high voltages, so we'll use a high voltage for both of those right there. And so that's a Q1, oops, right here. That's Q1 and Q0. Okay, and now our red light's on. So let's go ahead and watch our circuit run. It's green on the highway. We're waiting for a car to show up. A car shows up. We turn yellow for one cycle. Then we turn red. The car goes because he can go now. The highway stops so he can go. And then we're back to green again and we're stuck there. Now, we're tackling this manually. If we wanted to, we could grab a clock and delete that. And we can hook up our clock here to our circuit. And that way we won't have to toggle it. We could still toggle it manually by clicking it ourselves. But the cool thing is we go up to this simulate menu and we could enable our ticks. And now it starts clocking automatically. And we can make it go really fast. This would probably be really too fast for our stoplight right here. You can see it just kind of flows through because it gets back to 0, 0. There's still a car waiting, right? But that would probably be way too fast. We can slow it way down. We probably want a super slow clock for our highway. I don't even know if they make clocks. They probably have some sort of timer that goes off and then lets it go to the next state on real stoplights. But we're in the green state. A car comes. The car goes. And now we're in the green state again. Car comes. And now we're in the green state again. So we can see that our state machine does exactly what we want, and it can control the lights. Now we can connect this up to the opposite lights on the street so that, you know, when it's red on the highway, when they want to cross the highway, we can turn those green when it's red on the highway. Want to make sure that's right, or else if we give two green lights at the same time, we're going to have bad things happen. But this is how we create state machines. So I'll probably give you an engagement assignment when you watch this to practice creating a different state machine. and then we'll cover that in a Zoom meeting class, review it, and then you'll do this again for your control unit homework. And your control unit homework is you basically create one state machine and then you copy and paste a bunch of stuff onto your data path. So that homework, all you have to do is one state machine design for that, and then you get your control unit working. Thanks.